Okay.
Should we start?
Yeah.
So thank you very much for this kind of introduction, and it's wonderful to be again here in Cergy. I have never done a talk like this, but let's see how it will go. So you see the title of the talk. The title is Shannon's Entropy, Universality, and Beyond. And so this is not a talk about a single result or a set of results, but it's basically an introduction to a research program that is worked out in a collaboration with Giampaolo Cristodoro for University of Milan Bicocca, and with Mirko Delio Esposti, who is here in the audience, and he's also 2 months fellow at the Institute, and he's from University of Bologna, and with Renaud Rakepa, who is also here in the audience. He's a postdoctoral fellow at University of Cergy. He has graduated a year ago under joint supervision of myself and Alain Joie in the Cotutei between McGill at University of Grenoble. So a further testament to the collaboration between France and Canada. So in early stages of this program, we have also worked together with a postdoctoral fellow, Luigi Ripani. She was a Cergy McGill joint postdoc. She worked here in Cergy, was founded by Cergy, and she's currently a data scientist in the research and development group of Axion, I believe, located here in Paris. And we had 2 summer students, Xeniu Huo and Zachary Vernetz, McGill undergraduate students who worked with us during the summer under this summer research programs, undergraduate programs at McGill. Renaud also started many years ago to work with us within the same structure. So then let me start with the introduction. So as I said, so this talk is an introduction to an interdisciplinary research project at the intersection of information theory, dynamical systems theory, and probability from purely mathematical side. I'm a mathematician or better mathematical physicist, but it has applications, and these are very important applications from our perspective that motivated the program, to non-equilibrium statistical mechanics, but then to mathematical linguistics and mathematical biology. So these are the 3 applications that we are currently pursuing. And this talk is also serving as an introduction to the meeting that will start tomorrow. This is ANR. The name of ANR is Non-Stops, and then it is hosted here in Cergy. It will start tomorrow. It will last until Friday. And on this meeting, there will be lectures of Giampaolo, Mirko, and Renaud. Renaud will talk about non-equilibrium statistical mechanics. Mirko will talk about mathematical linguistics or linguistics, and Giampaolo will talk about mathematical biology. So these talks are sort of natural continuation of these introductory lectures I'm trying to give here. Now I should say that this program that we have here is a part of a broader research program that we have titled Beyond Gibbsianity at the moment. And here Gibbsianity means equilibrium. So you can say beyond equilibrium, that the structures emerge. That has been developed over the last 5 years, maybe more. The idea, maybe, I mean, we worked together for many, many years, but this idea beyond Gibbsianity started relatively recently from our perspective 5 years ago with my friends and collaborators, Armen Chirikian, Armen is here, and Claude Alain Pillet. So this is really sort of a program in which we put a lot of effort and whose basic form will be finalized, I think, this winter. And I will teach a research course on this program starting next week. So the organizational meeting is next Tuesday at 10 o'clock. The course will continue for 4 or 5 months. So I think if you're interested, we can provide you with additional information about it. Now, as I said, this is much broader program than what I will talk about today. I will hint about that during the talk. And there are complementary interdisciplinary aspects of this program. I think it's important because this institute emphasizes interdisciplinarity, and they will be discussed in the talks, I think, next Thursday by Francesco Ticozzi from University of Padua, who will talk about quantum engineering, a quantum control theory part of our program, and by Felix Rico, who is a biologist who is at University of Marseille, and who will be talking about protein unwrapping. And then there is mathematics of the protein unwrapping, the mathematics of how the proteins break, not just how they fall, but how they break. And you can hear about that from his perspective, which is purely experimental, that he on the next Thursday. Now, the program that we are introducing here, and that we'll have next 4 or 5 months to sort of structure properly, completely, will be also discussed in the talks by Noé Cuneo and Clement Tauber, parts of the talks, parts of the program, better to say. And I should emphasize here that both Noé and Clement were postdocs here in Cergy, and now they have a permanent positions. Noé is a maître de conférence in Paris 7. Clement Tauber is maître de conférence at University of Strasbourg. And the projects, what they will talk about is actually what they have started to work here in Cergy. Now, the final part of the introduction here is a short disclaimer. It is that, I mean, the talk will have 2 parts. The first part is this 1-hour talk that Flora has mentioned, that I try to reach the broader audience, and then I will not assume much, basically just a high school probability. And then there will be a second part of the talk that we will have after the break that will be also recorded, but it will be technically a little bit more advanced. And then in that part of the talk, I will make an introduction, the full introduction to the research program, and also an introduction to what will be discussed in the ANR meeting starting Wednesday. All right, so let me start with one slide of mathematics, one slide of annotation. So the starting point is a finite alphabet, finitely many letters, that sort of labels the outcomes of the probabilistic or stochastic experiment under consideration. And very often the alphabet will have only 2 letters, 0, 1, or you can think about them as a head and tails. And you can think about probabilistic experiment where you toss a coin, and then that coin is either head or tail. It's a random outcome, and that is one most basic example of probabilistic experiment you can sort of have in your head as an intuition for what is coming up. Now, the experiment is probabilistic, so it comes with a so-called probability. So probability is a number that you associate to the outcomes. It is bigger or equal than 0. And when you sum over all possible outcomes, probability of the outcome of A, you get 1. So if you toss a coin, the possible outcomes are head and tail, and probability of getting head or tail is equal to 1/2 if the coin is fair. If the coin is not fair, then you might have a different probabilities. Now, just a word about support of P, because I'm going to use that later. So the support of probability P is the set of all outcomes where probability is strictly positive. So this is where the probability lives. It sort of does not really see the outcomes where probability is equal to 0, but some other probabilistic experiment may see it. And so one needs to keep this when one combines several probabilistic experiments. P is called pure if probability of some letter of some outcome is equal to 1. So you can think that you have a coin which has 2 heads. Then whatever you do, when you toss it, you're going to get a head. So it's not really random. So P pure means pure is really not random, that one event always happens and none of the other events ever happens. Now there is an opposite case, which is sort of the most random case intuitively, that P is called chaotic if probability of every outcome is the same as it's exactly 1 over the size of our alphabet, which in this case is the letters. So right now, you can call it also uniform, sort of it's the most intuitive, the most random setting that you can have. And if you toss a coin and it's a fair coin, then you get 1/2, 1/2. That would be an example of a chaotic probabilistic measure or experiment in this notation. But there's one more thing that I will introduce here, and that is a notion of marginals, namely that if our set A has a product structure, namely it is product of A1 cross A2 consists of a pairs of letters, then P1 and P2 will denote the marginals of P controlling the stochastic experiments. So the marginals means, P1 marginal means that although I have outcomes which are pairs, I care only about the outcomes that are in the first letter, with respect to the first alphabet. So I just sum up over all possible outcomes in A2, and I fix on one single outcome in A1. And that defines P1. So basically, you just erase information from part of the system and focus on information that you have in A1, or you can call it the left part. And same with P2. You just erase the information from the left part and you focus on what is going on A2. So this marginal, this notion of the marginal, which is sort of basic probabilistic notion, will play a role in the part of the talk. So now the main subject of this long lecture, because I will talk hour now, and then after a break, hour and a half, is the entropy. So in thermodynamics, where it first appeared, it goes back to 1850 and work of Clausius. And the work Entropies actually goes back to the Old Greek, to the, I don't know how to say it in Old Greek, entropy, which is, how do you say it in Old Greek?
Entropia.
Entropia, which means transformation, right?
Yes.
And it refers to the transformations of the thermodynamical states of the systems that Clausius used to introduce entropy. Clausius was very much influenced by the works of, now in France, of course, the French military engineer in the army of Napoleon, Sadi Carnot, who worked on the efficiency of thermal engines. It's an absolutely beautiful work, and sometimes Sadi Carnot is considered as a real father of the science of thermodynamics, that his work goes to the beginning of the 19th century. So if you look at Encyclopedia Britannica, Carnot definition, not Carnot, but Clausius' definition is summarized as follows, that entropy is the measure of a system's thermal energy per unit temperature that is unavailable for doing useful work. So this is sort of the starting physics or thermodynamical definition of what entropy is. It's not a mathematical definition as written in these two sentences. Its statistical interpretation is due to Boltzmann, Gibbs, and Maxwell, basically shortly following the work of Clausius. And the next week, the talk of Clement Tauber will touch on these topics. So this was one really basic scientific revolution, thermodynamics first, and then statistical mechanics, statistical interpretation of entropy based on the atomistic picture of the matter. So it is a subject in itself. It is impossible to talk about entropy in a complete way without touching on thermodynamics and statistical mechanics, but I will not do that. Not here, at least. It is certainly part of our research program. What we will focus on is how entropy appeared in information theory. And there it goes back to Claude Shannon and his fundamental 1948 paper, A Mathematical Theory of Communication. So Shannon basically approached the concepts from completely different angle, rediscovered the formula for entropy that goes back to Boltzmann and Gibbs. But because of his completely different approach, he was not doing statistical physics. He was interested in the transmission and compression of information. What he has achieved is basically completely complementary to the advances that happened in the 19th century. And it also staged a revolution, different kind of revolution, that is sort of affecting us all, because what he has introduced and is sort of has been sort of the core of the technological revolution that follows in 50s and 60s. Now, beyond the information theory, one can make an argument that entropy is one of the most used and most abused scientific notions. So my son, because he knows I'm working on entropy, found for me a song called Entropy by a certain band that's called Awkward Marina. I don't know whether it's interesting to listen to a song, because I personally don't like it very much, but it had millions of hits. And I guess one can attribute those millions of the hits to the title. And then one continues, but in the literature, there is one very famous sort of phrase about the entropy that goes to Russian writer Anton Chekhov, who says that only entropy comes easy. And I think this is sort of something that one can try to convey to the people who are not mathematicians. So basically, why entropy comes easy? So think about your house and you stop doing housework. Then the mess will start to increase. And that is the increase of entropy. That is sort of second law of thermodynamics. The mess increases, the chaos increases unless you put work in. Now, eventually you reach a state of equilibrium. That was my room when I was a teenager. When the room is such a mess that nothing happens anymore. You remove one thing, but you put another one and the mess stays in a steady state. So the only entropy comes easy, meaning the disorder around us is increasing unless you put an energy to stop it. And in that way, anybody understands what entropy is and what second law is. On the other hand, from the scientific point of view, to give a proper scientific basis to the notion of entropy, and then to explore, to make applications of this notion and use of this notion, is arguably one of the most major scientific revolutions that we have witnessed. There are others, relativity, quantum mechanics, and so on. So we will take a Shannon's road, as I say, in this talk, and in the second part of the talk, we will follow the 1948 insights of the young Shannon. He was 32 years old when he wrote the paper. And here is, I think, Shannon at the time when he was writing the paper on his unicycle, doing juggling. He also had a paper on juggling. He was master of juggling in the later stage of his career. And one of the stories is that he was on his unicycle juggling and biking around Bell Labs. And that's how he was thinking about the paper he was writing at the time. And in that paper, he discovered the following formula, or introduced the following formula. We'll spend time on this formula. What is the entropy of stochastic experiments that is controlled by the probability measure P? Well, that's a non-negative number that you obtain like follows. You look at probability of event A, of an outcome A. You multiply this probability with a logarithm of the same probability. You put a minus sign and you sum up over all possible outcomes. So the simplest example is you toss a coin, then with probability 1/2, you get a head. With probability 1/2, you get a tail. Then you sum up these things, so it is 1/2 logarithm 1/2 plus 1/2 logarithm 1/2 minus logarithm 2, and then with this minus sign, it becomes a logarithm 2. So the entropy of tossing a coin, fair coin, is a number logarithm 2. But now what logarithm you have to fix a base of the logarithm? The base of logarithm corresponds to the choice of units. And we will take the base to be 2, because that's what you do in information theory, in which case the entropy of tossing coin is exactly equal to 1. So when you fix a base 2, then the units are called Shannons. When you take base 10, they're called Hartleys, and sort of you can pass between the units as is suitable to the problem. In statistical mechanics, it's natural to take for the base of the logarithm for the unit the Euler number E. So the entropy, the intuition behind that, is the measure of the randomness of the stochastic experiment described by P. So to sort of think about that, sort of basically you can have a coin that has both head and head. So you toss it, there is no randomness. In that case, you get a head with a probability 1, and entropy of that experiment is equal to 0. Or you have a fair coin, when you toss it, you get a head or tail with probability 1/2. And in that case, everything is random, and the probability, the entropy is equal to 1. There is another sort of synonym for this one, that entropy is the measure of informational content of the stochastic experiment described by P. So this is a little bit, one has to explain this properly. So in this setting, you toss a coin and then you cover it. So you don't know what the result is. And the question is, after I lift my hand, what did I learn by looking at the outcome? How much I learned? Now, if the coin has two heads and I toss it and I cover it, then I know I'm going to see the head. I learned absolutely nothing. But if I had a fair coin and I don't know whether I got head and tail, and then I lift my hand and I see it's a head, then I learned a lot because I had no idea whether it's going to be head or tail. Now you can have situation in between. You may have unfair coin where probability of seeing a head is 1/3, probability of seeing a tail is 2/3. So then you are in between, then it is more likely to see head than a tail, and then sort of you need sort of to quantify these basic intuitions in some way. So here are the basic properties of entropy written mathematically. So it's a real number. This real number is always positive or bigger or equal than 0, and it's always less or equal than the logarithm of the size of our alphabet. If our alphabet was 0, 1, then this would be logarithm of 2. Entropy could be 0, but it is 0 if and only if for mathematicians that means it's equivalent to that P is pure, namely that P gives probability 1 to one event and 0 to all other events. So if you have this completely deformed coin with head, then entropy is equal to 0. And that is the only possibility for entropy to be equal to 0. And the maximal value the entropy can have is the logarithm of the size of the alphabet. And that would happen if P is chaotic, if it gives the same probability to the all events, same probability 1 over the size of the alphabet. And in the case of our coin, that was the probability being equal 1/2, fair coin. In that case, entropy was equal to logarithm 2 or 1 because we take a logarithm in the base 2. Now the entropy map is continuous, so that means that if I change a little bit probability measure P, I change a little bit the entropy, it follows from the continuity of the function x logarithm x on the interval 0, 1. Now this is a little bit deeper. The entropy map is concave. That again follows basically from the concavity of the logarithm. And so what this concavity is saying, that if I take a mixture of probability measures P1, Pn, if sort of take a mixtures of the probability experiments, and this mixture is controlled by these coefficients P1 to the P of n. So these are non-negative numbers summing up to 1. These are mixture coefficients. Then probability of this mixture is bigger or equal than mixture coefficient times probability of entropy of P1 plus the mixture coefficient times the entropy of P of n. Mathematically, it is just a statement that the function is concave. Now, the slightly more interesting from our perspective, actually much more interesting, although property concavity is really essential in the foundations of statistical physics, but in the context of this talk, 4 and 5 are much more fundamental, is that the entropy map is almost convex. This is the way sort of chemists probably thinks about entropy. So here you have again the probability of the mixture. Now that here we had, sorry, you have to get used to this. Here we have a sign that goes bigger or equal. Here we have the sign that goes less or equal. So the entropy of mixture is less or equal than P1 entropy of P1 plus P of n S of P of n, entropies of individual ingredients that you have here, but then plus entropy of the mixing coefficients. So S of P1 to the P of n, small p is just minus sum of Pk logarithm P of k. And here you have equality if the supports of Pj's are disjoint. If the measures Pj, if the stochastic experiments do not see each other, if they live on a disjoint parts of the set of outcomes. So if you have equality here, then one can say that entropy of mixture is a mixture of entropies. And that's, I think, how chemists thought about the entropy before any statistical mechanics and so on. You can think about P1 and P of n as being some substances weighted by the P1, small P1, P of n that are mixture coefficients. And then entropy of the mixture would be just mixture of entropies, namely you weight entropies of the substances by the coefficients, and then you take the entropy of the coefficients that appear in the weight. The entropy is also subadditive, and this is another absolutely crucial property, namely that if A has a product structure, and then you take a probability measure P with the marginals P1 and P2. Well, taking marginals means that you have two systems, maybe you have two systems and you raise the information from this system by taking a marginals here. By taking the marginals here, you erase the information about this part. So by erasing information, you basically you erase correlations. That anything that you have sort of connected disappears because you took a margin. That means that intuitively, and it's sort of when you think about that, becomes quite intuitive, is that the product of the marginals is more random than the starting probability measure, because simply you erase any interdependence between part 1 and part 2 that was originally contained in P. So that is the intuition, but mathematically this is just a statement that entropy of P, according to our formula, is less or equal than entropy of the product measure, which is just sum of the entropy of P1 plus entropy of P2. And you have equality if P is exactly equal to P1 times P2. So initially, there were no correlations between left and right part of the system, of 1 or 2 part of the system. All 4 properties are completely elementary to prove, and sort of it's a high school. If you know the properties of the logarithm, if you know the graph of the logarithm, then you can just prove from 1 to 5. And they all go back to the paper of Shannon, to the 1948 paper of the Shannon, in precisely this formulation. But now, sort of you can say, so this is all well and nice. All the properties that I have here are intuitive. That's what I sort of expect entropy to satisfy. But is this the only function that you can have? Kind of, it looks a little bit strange. It is the only possible choice that one can have for entropy. Maybe some other function would do the same job. And actually here there is a drawing from Penrose's 99 book, God has, Emperor Has a New Mind. And so there you can see the drawing of God picking out the special low entropy initial condition of our universe. So the idea is that Penrose discussed it in detail, and of course entropy has its role in cosmology, is that in order that we have observable universe as it is, according to the laws of physics that we know at the moment, then at the moment of the Big Bang, the universe had to start in a very, very low entropy state. And that low entropy state is actually almost infinitesimally low. And he does the computation what it is. He gives an estimate how low it has to be. But if that is so, then this low entropy has to be computed according to some formula, to some rule. And this is the rule by which one computes it. So this formula goes to the moment of creation. So that has to be a natural reason why it is right, if it is to be used in this generality. And this sort of naturalness is sort of same as the naturalness of geometry. Sort of Euclid formulated the entire geometry on the basis of 5 axioms, and then one continues, right? And so the idea, which is quite non-trivial, because you can think a kind of, it went to Euclid, so people should try to do it in the science in different contexts, but using it in this context, it sort of requires a sort of a really real insight, and the insight is due to Shannon, to 1948. The formula was known before to Boltzmann and Gibbs, but nobody thought that one can try to axiomatize this formula on the basis on a few basic intuitive properties that any entropy function should have. So in the chapter, section 3 of his 1948 paper, the Shannon gives the first such axiomatization, that this formula is forced on us. We have no choice. Sort of if entropy is to be what one naturally expects it to be, the measure of disorder, then this has to be true. You have no choice. You have to choose this function. That's non-trivial, right? Because you can see there are so many functions in this world. Kind of, if I want to look just at the 5 basic properties, I should be able to find some other functions. And for 1, 2, and 3, the answer is yes. But 4 and 5, no. Each of 4 and 5 uniquely specifies the form of entropy. All right, so right now I assume that people have an idea what axiomatization is. So how this will work? So basically you take the set of all possible probability measures. So this is the union over all alphabets of A, all possible outcomes, and then you have probability measures on those outcomes. And we have a function that takes those probability measures, those description of stochastic experiments to 0 infinity. And we want this to be our putative entropy function. So we will assume something that is obvious, that one sort of does not need to say much, but remember, Euclid also has a bunch of axioms that are completely obvious. If point X is identified with a point Y is identified with a point Z, then X is identified with a point Z. So a lot of axioms sort of in Euclid are sort of completely automatic. And here there are 3 automatic axioms, is that entropy of stochastic experiment does not depend on the enumeration of the alphabet A. Are you gonna put, instead of head or tail, 0 and 1, the randomness does not depend on that, right? So to what letters are you gonna use will not affect the notion of entropy. So that's the first requirement. The second requirement is that if I enlarge my set of outcomes by one more outcome B and extend my P to A prime by setting it to vanish in this new outcome B, then I have exactly the same probabilistic setting. I just have a new artificial outcome that my measure does not see. And so this artificially extended probabilistic experiment should have the same entropy as the original one. And the third requirement in this entropy map is continuous. This you can relax considerably, but that is irrelevant for this talk, that if you change probabilities a little bit, you change this putative entropy map a little bit. And so here is the first axiomatization. So the first axiomatization, and that you suppose that in addition to these obvious things, the putative entropy map also satisfies what we call entropy of mixture of entropies, that whenever the supports of Pj's are disjoint, then entropy of the mixture P1, big P1 plus Pn, big P of n is linear combination P1 of entropy of P1 plus P of n, putative entropy of P of n, and then putative entropy of the mixing coefficients. So this is sort of, you adopt this chemistry picture of what entropy should be, although Shannon wrote it in a slightly different way. Then that's it. Then the only possible choice is that up to choice of units, you must have that this entropy function is exactly what we have written before, sum over P of A logarithm P of A. C is just setting up what the constants, what units are, and that you cannot see from this requirement. That is natural. And this is basically the axiomatization due to Shannon, that entropy of mixture being a mixture of entropies, in this sense, uniquely fixes the entropy function to be up to choice of units minus P of A logarithm P of A, sum over all events A. Now, the Fadeev and Khinchin and the Russian school picked up on this axiomatization. There are many refinements. I mean, so, but in spirit, it's always the same. That's entropy of the mixture being a mixture of entropies uniquely specifies the entropy function. The proof is not that hard. It can take 2 pages or something like that, but you don't need to use any fancy mathematics. It is elementary mathematics. The second axiomatization is, I think, actually foundationally deeper than Shannon's one, and it fixes the entropy function by subadditivity requirement. So we assume that this putative entropy function, in addition to the obvious requirements that we have introduced, is also subadditive. Namely, that if our set of outcomes has product structure, and we start with a probabilistic experiment described by P, and we have marginals P1 and P2 that arise by raising information from left and right, then putative entropy of P is less or equal than putative entropy of P1 plus putative entropy of P2 with equality if and only if one has a product. Then again, you have no choice. Then this requirement only fixes it uniquely up to a constant, and you get the formula that we have written before. Now, this result is established in 1973, took about 20 years of research and various refinements to come to the proof. So it is quite deep. Maybe it does not involve complicated mathematics, but the construction is rather elaborated. And just to say, kind of starting with Shannon's 1948 paper and the idea to have axiomatization in the first place, just to sort of try to axiomatize this formula in the spirit of Euclid, has led to an independent research direction. Some people spend some time on that, some people spend their entire lives. And there is an early book by Assel and Darab, I cannot pronounce their name, they're both, I think, Hungarians, on measures of informations and their characterization. It's a beautiful stuff. A lot of beautiful and deep mathematics come out from the attempts to understand in Euclid's spirit why we must have this formula. And we understand it, I think, quite well at this point. Now, Shannon was the one who introduced the axiomatization. He was the one who said there have to be the set of basic axioms from which the formula follows. And here is a picture of him actually playing with his famous mouse. It was the first artificial intelligent device, I think, that I know of. And his comment is very interesting. He says that this theorem, the axiomatization, and the assumption required for its proof are in no way necessary for the present theory that he develops. It is given chiefly to lend a certain plausibility to some of our later definitions. So the real justification of this definition, however, will reside in their implication. So Shannon has a degree both in mathematics and engineering. And it's sort of was hard to say when he is an engineer, when he is a mathematician, although I think that he has seen himself as a mathematician. So this axiomatization for him was just an introduction. We have this definition. Now, what do we do with it? Well, there will be some implications. And what is the implication? Now, this is a revolutionary implication. It is that the entropy provides the universal optimal bound on the compression of information. If you want to compress information, this is the best you can do. The entropy provides a bound that you cannot beat the disorder by compression, but you can reach it. And that is the entire subject of the coding. And then he follows on this with another remark that the main point at issue is the effect of statistical knowledge about the source in reducing the required capacity of the channel by use of proper encoding of the information. And that is what I have summarized here in a different language. This is a little bit, uses the lingo of information theory and lingo, engineering lingo. Here I sort of try to put it in a different language, except that I have omitted here the statistical knowledge about the source. You can add it, but the punch line of what I'm trying to say here, or what I will try to say next 2 hours, is that this statistical knowledge is, you could put it here, but you can also remove it. So we sort of have a really nice structural result. The entropy is imposed on us. But now what do we do with that entropy? And that's what Shannon insisted on. He didn't stop by introducing the concept of entropy. He wanted to have implication of this concept, and the implication is on the compression of information. And so right now we need to go a little bit deeper to understand what and how Shannon in 1948 has used the concept of entropy to achieve this revolution. And that will involve slightly more advanced mathematics beyond high school. And then after I introduce what Shannon has done in sort of, I think, still an elementary setting, the level of basic undergraduate level of education, then we can go and introduce the program that we are working on. So I think I will stop now because I don't want to bother you with what dynamical system is and so on, and we can make a break if that's okay with everybody. And then after the break, we can continue with the second part. So I should also say that we are staying here for a long time. So if any of you has a question, or if you're watching and you want to ask us about entropy and you think it can fit somewhere in your research program, in whatever it is, just let us know, and Mirko, Renaud, and I will be happy to talk with you. Okay, so thank you very much for coming to the second part of the lecture, which is going to be a slightly more technical, not too much, let's hope, because I'm still hoping to continue with a general tone that I have set up in the first part of the lecture. So just to remind you, we stopped at the revolutionary implications that Shannon had in mind about the universal optimal bound on the compression of the information that the concept of entropy has, that he introduced independently of, mentioned a few times, Gibbs and Boltzmann. So there was this main pointed issue that we also mentioned, and to which we will come back. So I'm not going to repeat it. So we will come back to what are the real meaning of this one sentence actually from his paper. So I will set up now a further notation. So A was our alphabet. So A to the power n is just n-fold Cartesian product of the A itself. So this n-fold Cartesian product contains of the n sequences, of the sequences x1, x2, xn, where xk's are the letters from the alphabet. And sometimes it is convenient to actually write this collected sequence x1, x2 to the xn as just a word. So the first letter of the word is x1, the second letter of the word is x2, the final letter of the word is x1. So the collection of the n elements from the alphabet is just a word, x1, x2, xn. And people in information theory use this shorthand, which I found very convenient. People in statistical mechanics do not, that x index 1 to the top n is just x1, x2, xn, or x1, or collection x1, x2 to the xn. Now, omega will be the collection of not finite words, but infinite words. So technically, omega is the collection of all sequences indexed by natural numbers, which takes values in our alphabet. So such a sequence could be written as an infinite word, but the first letter is x1, the second letter is x2, the nth letter is x1, and you go on. Now, this collection of all sequences, or the collection of all infinite words, is equipped with a map, which is called the shift map. And so what does the shift map does? So you take an infinite word, x1, x2, x3, and so on, and you map it to the word where you just erased the first letter. So x1, x2, x3 goes to the word x2, x3, x4, and so on. Now, sort of, I will just mention a little bit technical word, that if you equipped A with a discrete topology and omega with an induced product topology, then omega is a compact metric space, and the shift map is a continuous surjection from omega to omega. So you get a dynamical system, omega phi, omega compact metric space, and phi a continuous surjection from omega to omega. So this is arguably the simplest dynamical system that one encounters in modern dynamical system theories. There is one simpler, which is just a rotation on the circle, and that one one starts with when one teaches a course. And this will be the second one, which is maybe a little bit more complicated to introduce, but then has many, many more applications than rotations on the circle. So it's a really basic object of a dynamical system theory, but it's also a basic starting object of information theory, if you would like to sort of do it in a mathematically sort of sound way. There is another word that one uses here, and that is ergodic discrete time statistical source with values in A. This is sort of, you can think about this sentence you can find in Shannon, but what does it mean is that you just pick an ergodic probability measure P on this dynamical system, and this ergodic probability measure captures the entire statistics of this ergodic discrete time statistical source. So these are the synonyms. Do you have the distribution, the statistical distribution of such a source is ergodic probability measure on omega, and everything that you want to know from statistical perspective about this source is captured by this probability measure P. So just a word about probability measure P on omega. They're always assumed to be Borel probability measure. They're uniquely determined by the sequence of their marginals. So the marginal of P is that nth marginal of P is the restriction of P to the first n letters of the alphabet. And collection of these marginals uniquely determines P. You need consistency relation here if you sort of want to go backwards from Pn to P, but this is not important for this talk. So basically to P, we associate in a unique way the sequence of the marginals Pn and the sequence of the marginals P of n. If I know how P acts on any finite sequence of the letters, then we know P in general. Now, when I showed this slide to my former postdocs, one of them, Tristan Benoit, said that I should actually have one slide elaborating what is ergodic. So I added these slides here, so it's just a note on ergodicity. I don't think you're going to learn about ergodicity from this slide, but sort of you may have an idea and then just look in the books or internet what ergodicity is if you have not seen it before. So the measure P is shift invariant. We have introduced our shift map if the probability or value of P on a set F inverse of E is equal to P of E. So this is how measures change under the transformation. You apply P on a set that is inverse image of E. So if the set is shift invariant, then it is called ergodic if the inverse image of E is equal to E under the shift map. If the set is invariant under the shift according to this definition, then the probability of E is equal to 0, 1. Now there is a way you can think about this. So this relation that F inverse of E is equal to E means that if I have a subset E of omega and I pick point X in that set, and then follow it by my dynamics phi. So I have X, I have phi of X, phi square of X, phi cube of X, and so on. So I have a dynamical system trajectory. If this trajectory never leaves E, if this set E is invariant under the trajectory flow, then this set is either empty set or the entire space according to the measure phi. So basically, your trajectories of the system have to move around your entire space in a particular fashion. Not only they have to be dense, but they really have to be sort of filling the space in a way that this condition here is satisfied. And this definition of ergodicity goes back to Boltzmann, by the way. It's also a Greek word, but now I forgot actually how. Maybe Flora can tell us how do you pronounce it correctly. Now, there is another way of looking to ergodicity that goes back to Birkhoff, or the statement is the Birkhoff ergodic theorem, that the shift invariant P is ergodic if and only if, for any continuous map from omega to R, we have that average over the values of F along the trajectory of our dynamical system. That's what I have here, 1 over n, sum from j is equal 0 to n minus 1, and we evaluate this sample function, this random variable, on the points phi j of x as we go along the trajectory of the dynamical systems, and then we take the limit n is going to infinity, is exactly the phase space average, namely the integral over omega of f dp. You can start with this as a definition of ergodicity. This has to be true for every continuous function f and for p almost all choices of x. So it is sort of an intuitive definition, and also sort of, you can see that ergodicity is an ultimate form of the law of large numbers. So after this digression to ergodicity, we return to entropy. So we'll discuss first the specific entropy, and our starting point will be always an ergodic source. So an ergodic source is an ergodic probability measures on omega on the set of all infinite words with the letters from our alphabet. And then we know how to define the entropy of nth marginal, because the nth marginal is the measure on the finite set. Nth marginal is a measure on the set a to the power n. It's a finite set. And then the stationarity of P, we don't have to use ergodicity, we just need to use that P is stationary under phi, gives this remarkable relation, which is also not only stationarity, but you also use subadditivity, that if you look of the entropy of n plus m marginal, you get inequality that it is less or equal to the entropy of nth marginal plus entropy of the mth marginal. So here you use a subadditivity to derive inequality, and then you use a stationarity to get this precise form. Now, once you have this relation, the subadditive relation, then you have automatically the existence of this limit, 1 over ns of p of n as n goes to infinity. And the value of this limit is also equal to infimum of n bigger or equal than 1, or 1 over ns of p of n. So this relation here is an exercise. I always give it in analysis 1 course, honors analysis 1 course at McGill. It is a consequence of something that is called Fekete lemma, has 4-line proof. And the value of this limit here is called the specific entropy of the source P. So sort of the specific entropy is sort of the entropy of the marginals per size of the system, and the size of the system is measured by the length of the length. So this is also for people who are familiar with the language of dynamical system. This is also in this setting the Kolmogorov-Sinai entropy of P. It has many magnificent properties, but I will mention just one, that it takes the values between 0 and the logarithm of the size of the alphabet. That's where the normalization comes in, that it does not explode, but remains finite in the limit. So the specific entropy is the basic notion in information theory, dynamical system theory, probability, statistical mechanics, and then in all other applied fields that make use of the theoretical advances of more theoretical fields I have mentioned here. And so we come now to the first Shannon's theorem. So what did actually Shannon, I mean, I will not follow exactly neither the notation or exposition of the Shannon, but this is, I will try to summarize what are the basic results, and also sort of, I use the terminology that I have invented. I mean, you may not call it a first Shannon's theorem. I mean, you can call it noisy coding or whatever. I mean, for us, it will be the first Shannon's theorem. So we start with some input. So the input is, we start with the ergodic source, P, which is uniquely specified by its marginals. Then we need a compression alphabet, the alphabet in which we are going to do the coding, and the compression alphabet we take just to be 0, 1. Then we fix some epsilon between 0 and 1, and this epsilon will be our fixed allowed coding error. So we will be coding, but we will allow to have some coding errors as we proceed. And we fix two natural numbers n and m. Now, coding pair is a pair of two functions, Cn and d of n. Coder is a function C of n, the function C of n, which takes a to the power n to the 0, 1 to the power n. So what coder does, it maps the words with letters from the alphabet A of the length n to the words from the alphabet 0, 1 of the length m. The decoder is the map that goes the opposite way. It will map the words from the alphabet 0, 1, sequences of 0, 1 of the letter of the length n to the words of the length n from our alphabet A. And now one can immediately introduce a compression coefficient. The compression coefficient is m over n. That means that we would like to shrink as much as we can the length of the words from A to the n, the length of the words the words of the length n with letters from alphabet A once we replace or map to the words with alphabet 0, 1. Now, a priori, you can make this coefficient as small as possible. You can take m equal to 1. You have to be reasonable in constructing the coding pair. And a reasonable coding pair should have a small error probability. So what is the error probability? Well, you take sequence x1 to the n, that's a word from A to the n, the word of n letters with the alphabet of A, and you code it with Cn. So Cn of x1 to the n is in this set. It's a word of m letters with the alphabet 0, 1. And then you decode it. Then you apply the map d of n to the coded words. If you don't get back x1 to the n, then, and you might not be able to because the cardinality of these sets might not be the same, then you made an error. And if that is the error, we would like to compute what is the probability of this error, what is the probability of all the words for which the coding is not exact. So if this probability is less than epsilon, then the pair NM is called epsilon good. So you would like to make this error probability less than the fixed prescribed error that we had in the beginning. Now, once I fix n and I fix epsilon, we denote by m of n the smallest number such that the pair nm is epsilon good. So the ratio mn over n is the best possible compression that one can have in this setting, subject to an allowed epsilon error probability. And then this is a Shannon's theorem that whatever error I fix, we of course want to fix error as small as possible, but it does not matter what do you do because the result is asymptotic. that for any epsilon between 0 and 1, limit n is going to infinity of the compression coefficient is of the best possible compression coefficient is exactly the entropy of our source. So the specific entropy is the universal optimal asymptotic bound on the compression of information. If you sort of do the coding in the setting that I have described, then this ratio is always going to be bigger or equal than entropy of the source in the limit. And if I choose M of n in the optimal way, such that the smallest possible number for which the compression, according to what we have discussed, is possible, then in the limit, I get precisely the entropy of P. So that was the first fundamental result of Shannon. And to prove this result, he actually needed another technical ingredient. It is much more than technical from the historical perspective. That is what is today known as a Shannon-McMillan-Brayman theorem. So Shannon-McMillan-Brayman theorem is a deep refinement of the convergence that we got so easily, namely the convergence that have defined the specific entropy. So this convergence can be understood in the following way. So you can form what one calls the entropy function. Namely, we take the nth marginal and we evaluate on the n letter word x1 to the n. We take a logarithm and a minus sign. So this is the function that I have here. It is defined, of course, for every x1 to the n in our a to the power n. If I integrate this function, then I get s of p of n. If I divide with 1 over n and take a limit, I get the entropy. So basically, from this formula, I pass to this one by integration. And then I know once I integrate, I will converge to the entropy of P. Now the question is whether I can actually interchange the limit and the integral, whether I actually will have a convergence here along the typical trajectory of our dynamical systems, namely for whether it will happen that you do not need to integrate, namely the entropy function itself for typical realization X will converge to the entropy itself. This turns out to be true. It is a profound result, which is central to Shannon's work and central to the proof of the previous theorem. You don't necessarily need this result in this strong form. You may have a convergence in probability, you may have something weaker, but you do need some variant of Shannon-McMillan-Brayman theorem in order to proceed with Shannon's theorem. So Shannon has proven this result in the context of Markov measures, Markov chains. And he proven the convergence in probability. So it is a simple, technically simple result. It suffices for what he wanted to do. Then mathematicians picked up on that, trying to improve it, because it was clear that once you have this type of convergence, that entire Shannon's theories work. And then you wanted it to work in as big generality as you can imagine. And it took about, I think, 10 years after the appearance of the Shannon papers to prove the result in this generality. I know 3 proofs of it. You can prove it by using martingale convergence theorem. So you cannot use just the Ergodic theorem. You sort of need to do a little bit more. So it can be proven by using martingale convergence combined with the Ergodic theorem. Another proof is to use the Kingman extensions of the Kingman subadditive Ergodic theorem. Sort of you use the subadditivity that one has here, but in a more profound way. And you can do that. I think that proof goes back to the Reniets, sort of I think in 1982. Then there is a third proof that I know of, combinatorial type, a very beautiful proof that goes to Ornstein and Weiss. So right now we have sort of many different ways of looking at this result. But in any case, it is really this type of the result is essential to Shannon's theory. You cannot avoid it. The type of the convergence that we have in the definition of entropy is not enough. This is very, very soft result. This is sort of an undergraduate level. But here you need to know a bit of advanced mathematics in order to prove it and understand it as well, because every proof gives a particular way of understanding this result. It's very deep. And connect with Boltzmann's picture of statistical mechanics, but I will not talk about it here. And now we turn to the second Shannon's theorem. And second Shannon's theorem, in sort of words, deals with what one can call lossless faithful variable length coding of the ergodic source. You can just forget about this. I'm going to define all the words, but sort of if you read the literature, this is what we will be describing here. So here we take beta to be the set of all finite length words with letters from the compression alphabet 0, 1. So you have words of the length 1, 0, and 1. Then you have words of the length 2, 0, 0, 0, 1, 1, 0, 1, 1. And we have the words of the length 3, 0, 0, 0, 0, 0, 1, and you continue so on. So B is an infinite set, which is mathematically written here, whose elements are just finite length words from the target alphabet. Now, a code sequence is the collection of one-to-one maps, Cn for every n, that goes from A to the n to B. Now, here is a big difference between the codings that we had before and the coding that we have now. Here, the letters, the words of the length n do not have to be mapped to the words of some fixed lengths. The lengths can vary because the images that we have here take values in the set B. So maybe one words of the length n will be mapped to 0. Another words of the length n will be mapped for some super long word that we don't know what it is. But so that is one difference, because on the previous construction we had a map from A to the n to the 0, 1 to the power m. So in the first Shannon theorem, the length of the length of the image words was fixed, but we didn't require that Cn is 1, 1. So we had sort of loosey codings. We could make an error. Here we do not make an error because sequence Cn is assumed to be consisting of one-to-one maps. Now, sort of for people who know the subject, usually one assumes also that these codes are prefix-free and develops theory for the prefix-free codes. And then one has a little result that actually for the asymptotic results, whether it's a prefix-free or it's 1, 1 doesn't matter. But since I will not go in such detail, I will sort of fix here on one maps and just make a remarks, this sort of a loosey remarks about the prefix-free codes. Now, once I have a coding, I can assign to a code the length function. So the length function of x1 to the n is the length of the code word Cn x1 to the n. So this code word could be anywhere in this set B. And so when I change my x1 to the n, when I change my word of the length n from the alphabet A, then I change also, in principle, the length of the code word. Now we have the expected lengths. Well, we just sum up the lengths of the words, of the code words of x1 to the n. So, and then we look at the probability that this word has appeared. So this is just expectation of this code function over the margin of P of n or over P, because it does not matter because ln depends only on the first n words. So this is sort of the expected length of the coded word according to the C of n. And you can also look at the ln itself. So what is a compression here? So the compression is measured by the ratios, either in expected way between expected lengths divided by starting lengths, or if we go along the trajectory, we look at compression of each single word with respect to the length n. How much we have affected the original length of the word by our coding. And these are sort of the other two Shannon's theorems. Sort of when I teach this stuff, I call them weak and strong. So the first theorem, or second theorem, if you take previous slides into account, is that you always have that this compression coefficient in the limit is bigger or equal than the entropy of the source. And there are optimal codes for which this limit of the expected length divided with n is precisely equal to the entropy of the source. And you have a second result, which is strengthening, that you don't need to take expectation values. Just kind of, you have an existence of entropy, and you have Shannon-McMillan-Breiman theorem. Here it is, there's an analogy here. Sort of, you say, okay, I will not going to take expectation. I'm going to look along individual words. So this is compression coefficient along the individual words. And then P almost surely, this limit is always bigger or equal than S of P. So the compression along the individual words is always bounded below P almost surely with respect to the entropy of the source, but you can achieve it. There are optimal codes for which actually this limit is going to be precisely the entropy S of P. Now, what is nice about this theorem, second theorem here, first implies the first one, obviously, by Fatou lemma. But secondly, for its proof, you have to use Shannon-McMillan-Breiman theorem. But it is actually equivalent to Shannon-McMillan-Breiman theorem. You can take this formulation here and then prove the Shannon-McMillan-Breiman theorem backwards. So this statement about the coding, and that is observation that goes back to Baron, I think, 1980s. It's an observation, but the proof is non-trivial. You have to do something. So it is just an equivalent way of understanding from the coding perspective what Shannon-McMillan-Breiman is saying. It's not that only the theorem is implied by the Shannon-McMillan-Breiman theorem, but it's equivalent to it. So once you have this result of the Shannon, this type of the coding, where you sort of, you do not have any error in a decoding, but you are coding with the words of different lengths. And the previous theorem that you sort of, you have an epsilon error in your coding, but you're coding with the words of the same length. I mean, there are optimal codes in the question. And so you would like to understand these optimal codes. The name of the game right now is we know that entropy is the best we can do. So how do we do it? How do we construct these optimal codes? And so one naturally expects that the construction of the optimal codes for which we have that these limits are saturated here, so in these two lines, would involve the knowledge of P. And many codes, especially codes in the beginning of information theory, are such. Shannon code, Huffman code, directly depend on the knowledge of our source P. And this is what, coming back to that paragraph or that sentence that from Shannon's paper that we ended up the first part of the lecture, that the main point at issue is the effect of statistical knowledge about the source in reducing the required capacity of the channel, compression of information, by the use of proper encoding of information. But this effect of the statistical knowledge is sort of necessary, because if I have to compress, I have to compress, the best I can compress is to entropy of P. But if I don't know what entropy of P, how do I know I'm compressing in the most optimal way? So basically, you have to know statistics of your source. You have to know your entropy. And then once you know statistics of your source, you can use it to construct the codes. So you change the source, you change the code. And that was sort of, that is certainly true in these two codes, in many other codes. You sort of use your statistical knowledge to construct optimal code. But what if you have no statistical knowledge of the source? Now that looks sort of even a crazy thing to ask. I have two halves here, I have to correct it. So if you have no statistical knowledge of the source, you have not even an idea what entropy of the source is. How would you ever even construct an optimal coding? And so this is the second part of universality, so sort of the title of entire lecture was universality. So we have first universality was why is the entropy universal? But now we have second part of the universality, which is going to do with the compression, with the Shannon's theorem. So the question that you can ask is, do there exist deterministic, universally optimal code sequences such that for any ergodic source P, we have optimality in the Shannon's theorem? That I either average or I look at a compression along the typical sequence and I get back entropy. So this is something remarkable if true, right? Because it means that if this is completely deterministic, does not depend on my of any randomness, then in particular I have a way to compute entropy of any measure, ergodic measure, any stochastic source, because I just have to look along the typical realization, how much compressions do I have. So naive intuition is something like that can't be true. And if it is true, it is astonishing. So it puts some effort to find sort of Shannon with a valid expression. I mean, sort of a mathematical physicist by training. So I mean, I do not maybe know the history of information theory that well, but in all what I have read, I have not seen that Shannon ever conjectured something like this. So that the universal code of this type or the universal characterizations of entropy of this type could exist. That sort of you have a deterministic prescription that will give you the entropy of any ergodic measure on your shift. And if it exists, it's astonishing. And if you think, I mean, one has to think about that. One can, once you know it is true, you can develop intuition why it should be true. But on the face value, it is an astonishing result. And this is possible. And then even if it is possible, you can ask, is it possible to do it in any reasonable way? And there is absolutely stunning way how it is done. And this is what is now known as a Lempel-Ziv universality. So here you can see Ziv, here you can see Lempel. I think it is some years after they have done their work. So as I said in the comment session, I mean, the work was done in the years 1977, 1978. They were basically motivated not by the application, but by the theoretical understanding of the concept of information, building further on the Shannon's work. It turned out that what they have done had a few years later had an amazing spectrum of application. They didn't patent their code because at that time it was impossible to patent such things. So some later codes got patented, and the entire history of the subject is fascinating, just like entire history of information theory is fascinating. So they have introduced those universal codes who have done exactly what I said, and they are based on what one calls these days, or Lempel-Ziv parsings. So once you understand the Lempel-Ziv parsing, understanding the code is just fairly routine, that the entire depth on the construction is on the LZ parsings. So I will not introduce the code because, you know, I will need additional 10, 15 minutes to do so, but you have to trust me that once you have the idea of parsing, then it is just, I mean, if you open the Shields book, it takes one page to go from the parsings to the construction of the universal optimal code. So how does the parsing work? What is this basic idea? So you start with the word of length n. So this is the word from our alphabet of the length n. And I will assume that my alphabet is 0, 1, just to sort of draw or to have an example. And this is parsed in such a way that every new word is the shortest word not seen before. So this is a very compact way of saying something that is simple, but it's confusing unless you have an example. So let me do an example. We take n is equal to 11. So here we have a word 1, 0, 1, 1, 0, 0, 0, and so on. So how do we parse it according to this prescription, according to Lempel-Ziv? So the first word is one letter word 1, because that you have to start. Now, what is the shortest new word that has not never appeared before? That's 0. It's one letter word. It's certainly not equal to 1. So we parse it. So that's a new word. Now, I cannot take 1 because 1 already appeared. So I have to take 1, 1, the next one, shortest one. And that indeed did not appear before, because before I have only one letter word 1 and 0. So after 1, 1, I cannot take just 0 because 0 appeared, but I can take 0, 0. So 0, 0 is here. Then I take 0, 1, 0, 1 is here. So after that, I cannot take 0. I cannot take 0, 0, 0, because 0, 0 appeared and 0 appeared. So the next word is 0, 0, 1. And that's it. So we now introduced a function, p of x1 to the n, which is the number of parsed words in x1 to the n. So it's completely deterministic procedure. We just look for a shortest new word as we go along the original sequence of zeros and ones. So in the above example, this was our x1 to the n, and how many parsed words we have? We have 6, if I count it correctly. So the algorithm is completely deterministic, and once you have this algorithm, then you describe the Lamp-Perceived code. I mean, it has a particular logic to it, but it's not that. I mean, once you have the parsing, the code comes out naturally. And here is a theorem, striking theorem, that for any ergodic source P, if I look at the number of the parse words from x1 to the n, of the x1 to the n, multiply with logarithm n, divide with n, this will convert to the entropy of P, both P almost surely, and in L1 of omega d. So the left-hand side is completely deterministic. This number does not depend on any measure. It is given by totally deterministic prescription. The right-hand side, of course, depends on P, and key here is that convergence is P almost surely, because there is no contradiction, because if I have two ergodic measures, P and Q, then they're mutually singular. They are supported on this joint set. So this is not a contradictory statement. So it has its practical application, but this is a mathematically a very deep foundational result if you read the proof. So the proof has two directions, less or equal and bigger or equal, and each of them comes with its own set of ideas. The proof itself shed a light what entropy is. So this I again repeat, amazing mathematical result gives the universal optimality of Lamp-Perceived code you're going to build. It's of independent interest because it gives you the universal way to compute entropy of any source. And it's now a different story for a different talk. Who knows subject better than me? What were these remarkable practical applications of these results? So the Unix, the first Unix decoders were based on Lamp-Perceived. It was used in there are many variants of the code that can improve its performance and so on. So right now, once you have it, one can sort of study it further. And the further studies of this LZ parsing that we have introduced have led to further deep and unexpected universal characterization of the specific entropy. So I will discuss two of them, but here the emphasis is, Lempel and Ziff were engineers, right? They were in engineering department in Haifa. They were also working in the BET labs, but the insights that they were made, whether mathematicians is a different story. If you read their papers, they're beautifully written, mathematically completely rigorous. It's really truly beautiful mathematics. So, but it was you would think that these things maybe would have come in physics, but mathematical physics, but they did not. And they have not had an impact on physics, to my knowledge. And that is one goal of our program, actually. So what is the second characterization beyond Lamp-Perceived parsing? It is the return times characterization, which is actually probably more physical len plus ziv parsing. So this is due to, again, Ziv and Wiener, which I think he was PhD student in 1989. And then it was complemented by Ornstein and Weiss, two famous mathematicians in 1993. They completed the proof, and they also added a new insights into the construction. So I need a piece of annotation here. So we start with an infinite word from our set omega, x1, x2, letters are x1, x2, and we can define a window in that word, which we denote xk to the n, which is just the words from k plus 1 to the m's positions, so or times, if you wish. So you just take a window of these infinite words going from k to the n. So the recurrence time function is here, but so right now everybody gets tired. So in the words, it is the first time the opening string x1 to the n reappears in x. So you look at your x, you look at the first n letters, and then you look when are those first n letters going to reappear again, but starting from index n, starting from the end of the string itself. So here is an example that actually Renaud wrote, and I just copied it. So I mean, I'm not going to read it, right? It's a long sequence of zeros and ones, and you take the first four letters. The first four letters are 0, 1, 0, 0, and you say when is the 0, 1, 0, 0 going to reappear in x? So here is 0, 1, 0, 0, and then you just look when it is going to reappear. It reappears right here, and the distance here is 5, and so this is going to be our infimum here. So R4 of x is equal to 5. So it's again completely deterministic procedure. It has nothing to do with anything. You just give me a sequence of zeros and ones, and I compute what Rm of x is. And the theorem is that for any ergodic source P, the limit n is going to infinity 1 over n logarithm of this return times is precisely the entropy of the source, and this convergence is P almost sure, and in L1 of omega dp. So again, absolutely stunning, unexpected universal characterization of the entropy. Left-hand side is completely deterministic. Right-hand side depends on the source, but we have a convergence P almost sure. And so this is, again, a mathematically deep foundational result. If one reads the papers, there is the original proofs are not that easy to read. But there is a simpler proof which introduced a completely novel strategy that is due to Kontoyanis in his 1998 Stanford PhD thesis. And this is a thesis which is really worth reading. It is a 50-page, 55-page thesis, has many results, many beautiful new ideas, and very, very accessible. So Kontoyanis' work has actually influenced our work quite a bit. So there is a third characterization, which we will call waiting times characterization. And that is also due to Wiener and Ziv, the same paper. Then there are many papers on the subject, right? But I mentioned here sort of a paper of Morton and Shields from 1995. It's a very mathematical and very difficult paper to read, but sort of established the best technical results we have at the moment about waiting times characterization. And then there is Kontoyanis' thesis from 1998, and I will come back to it in a second. So waiting times functions are defined now not in terms of a single infinite word x, but of the pairs of the infinite words, x and y. And so given x and y, the mathematical definition is here, but what does it mean? Wn of xy is the first time the strings x1 to the n, the opening strings of x of n words appears in y. So you look opening x1 to the n, in return times you look when it is going to reappear in x, and here you say, okay, but there is some independent y, I'm going to look when it is actually going to appear in y. And so here is again, thank you, for another sequence of 1 and zeros. And then here you again can take the first 4 ones, 0, 1, 0, 0. And now you don't look when they're going to reappear in X, but you say, when is this going to appear in Y below? And then you just look, okay, here is 0, 1, 0, 0, 0. And the first time it will appear, you can check that. It appears right here. So the waiting time is 5. How long you have to wait in the sequence Y before this opening strings X1 to the 4 appears? And then here is a theorem. Now we need the conditions under suitable mixing regularity assumptions on the P limit n is going to infinity 1 over n logarithm Wn of xy is again entropy of P for P cross P almost pairs X and Y. So this is again, I mean, you have to think a little bit about that. It's a little bit counterintuitive result. This is the first result that is not completely universal. So we need to make assumption the technically best result. So here I'm using the words, assuming that you know it. If you don't know, just ignore it. Or involves better mixing and is due to Morton and Shields. The proof is very, very hard. And there is a counter example that if you go beyond mixing, beta mixing to what people called very weak, I actually forgot the word, the same class of measures that appears in Ornstein isomorphism theorem, optimal class for Ornstein isomorphism theorem, which is very weak beta mixing. Ornstein isomorphism theorem is telling us when is dynamical systems isomorphic to Bernoulli shift. And in that class, there is a counter example that is due to Shields, and which is again very hard to construct. So these are hard results. But an elegant, simple proof in the case of psi mixing, and psi mixing would covers Markov chains, multi-level Markov chains, hidden Markov chains is due to Contoyaris. So this is maybe the first paper to read on the subject, and you can be discussed in Shields' book. And the two important messages are that that this is not completely universal, and it has a generalization to relative entropy. I will not discuss here at all, but sort of one of the reasons I have picked this result is that it is also important for its generalizations to the other entropies. So here the job is not finished. I think the precise boundary for which this result holds is not known. So for example, to my knowledge, even if you take an ergodic Markov chain, the simplest possible case, but not mixing, it is not known whether this is true, which is incredible. So I mean, so that would be maybe an interesting project for a student to verify whether if you take an ergodic but not mixing Markov chain, whether one have results like this. Anyway, it's there are important, presumably very difficult questions with regard to the last theorem. Not a completely universal result, requires assumptions, and all the assumptions involve mixing. So I finally come to the research program. So we come back to the first slide, basically. So the fundamental entropic laws of large numbers with respect to P almost sure convergence, should eliminate sure, we discussed so far are the following one. First, we have Shannon, Macmillan-Bramer theorem. This is not universal at all. So you give me a measure P, I form the entropy function, logarithm Pn of x1 to the n. This depends on P, and then you have a convergence, P almost sure. It is a fundamental result, it's a basic result, entire information theory a la Shannon is built on that, but there is no universality. The second result is this stunning Lamper-Ziv theorem that you can have a convergence to entropy for any ergodic source P, but with a completely deterministic description. Here is the number of the Lamper-Ziv parsed word in x1 to the n, multiply with logarithm n, divide with n, and this deterministic function converges to entropy of P almost surely for any ergodic measure P. In a similar spirit, you have the characterization of entropy in terms of the return times, that you have this return time function. The first time the opening string x1 to the big N reappears in X, you take logarithm Rn of X, divide with 1 over N, and that again converges to entropy P almost surely. And finally, this is again deterministic, but not completely universal, because it requires some ergodicity assumption that for the waiting times, the first time opening string x1 to the n appears in Y, 1 over n logarithm of the waiting times converges to S of P, entropy of P, P times P, almost sure. Now here, just to give it a justice, the Shannon-McMillan-Bramer theorem is used fundamentally in the proof of all three results. So you cannot get away from the Shannon-McMillan-Bramer theorem. You can just sort of use some implicit universality in that, which is not in the statement, in order to define, to prove those results. It's not that they are independent of Shannon-McMillan-Bramer theorem. They really sit on that. And that is particularly transparent in the proofs of Contoyanis. So here is the program. Once you have the laws of large numbers, you would like to go beyond it. So the first thing to do is to study the fluctuations, and that is the study of the large deviation principle. So here we have 4 laws of large numbers, and you would like to understand, okay, I know these are random, these are quantities here, so you have sort of convergence in the sense of law of large numbers. These are P almost sure convergences. So I would like to understand whether what are the fluctuations that accompany these limit theorems, and one knows that one learns a lot about those large deviation principles, about the statistical nature of the convergence in the laws of large numbers. The second thing is that one very closely related is to study the fractal dimensions of entropic level sets, to compute their Hausdorff dimension, and then relate this Hausdorff dimension to the large deviation principle. Then one would like to extend this universal characterization to other entropies, to Rényi entropy and the relative entropies. For the relative entropy, actually, this is part of it are implicit in the literature for the waiting types. For Rényi entropy, it is not in the literature, at least not to our knowledge, but we have sort of a clear ideas how to get to some types of the universal characterizations of Rényi entropy. And there are then applications of this program to non-equilibrium statistical mechanics. So that would be Renaud's talk, then linguistics, that's going to be Mirko's talk, and biology, that will be Giampaolo's talk. Sort of maybe they're more modest with this sort of over general scope of applications Flora would like to see, but that's sort of the way we approached it. And this is a long-term research plan. So we plan to have several postdocs, several PhD students involved into this program over the next 4 to 5 years. And there are first results. So actually, the first result, in a certain sense, goes back to a couple of years ago in the joint work with Noé, Godelan, and Armen, large deviations and fluctuation theorem for selectively decoupled measures in shift spaces. That was sort of, and that answered the question, at least the question to the, I think it is technically the best existing result in the literature about large deviation principle and the convergence that we are having here. And it had implications for the fractal or multifractal theory of the same convergence. And that multifractal theory is discussed in the second paper. And actually, I don't think Renaud will talk about that. And there is a third paper, which is also just being finished, about the applications of these notions to the non-equilibrium statistical mechanics. So this is, I mean, we have been seriously delayed like everybody else by the COVID crisis. But I mean, late in finishing the papers, but they will be available soon on the archive. And this is just the beginning. As I said, hopefully many more to come. As I said, this is a long-term research project. It's just the first steps that we are making in that directions. And so continuation of this talk, for those who are actually watching this video, will be on Thursday, this Thursday. Mirko will talk about entropy in language, natural and artificial. And then immediately after Mirko, Renaud will talk about, title is a program on limit theorem for entropy reproducing random variables. They're 1 hour talks, so they will be able to say a lot. And then on Friday, Gianpaolo will turn to the biology and talk about symmetry and structure in genetic sequences. So we are trying to learn from each other. Some people have expertise in one direction, some people have expertise in the another direction. So I think that is the definition of interdisciplinary. And then there is a course I will be teaching starting next Tuesday. We will be recording, and anybody who is interested can send me an email, and then we will add you to the list. So thank you very much. And that is it. Recording.